The chip inside the latest iPhone contains more transistors than there are stars visible in the entire night sky from Earth. Not comparable, more. Roughly 100 billion transistors, each one switching on and off billions of times per second, crammed into a sliver of silicon you could lose under your fingernail. And here is the part that stops most engineers cold when they first hear it. The smallest of those transistors is about 2 nanometers wide. A strand of human DNA is wider. You are not dealing with miniaturization anymore. You are dealing with something that operates at the boundary of physical reality itself. This is not an abstract engineering curiosity. The race to shrink transistors is the single most consequential technological competition happening on Earth right now, and most people have no idea what it actually involves or what breaks down when it stops working. In 2024, TSMC, the Taiwanese company that manufactures chips for Apple, Nvidia, and AMD, reported revenues of over $90 billion. That number will seem small in retrospect, because the entire global economy, meaning AI, medical devices, electric vehicles, financial systems, military hardware, is now structurally dependent on a manufacturing process that only 3 companies on the planet can perform at the leading edge: TSMC, Samsung, and Intel. If that supply chain fractures, and it very nearly did in 2021 during the chip shortage, new cars stop being built, hospitals lose diagnostic equipment, and defense contractors halt production. The stakes are not theoretical. They already materialized once. They will again. To understand how we got here, go back to 1965. Gordon Moore, co-founder of Intel, published an observation that became a law. The number of transistors on a chip doubles roughly every 2 years, while the cost per transistor falls. For 6 decades, the semiconductor industry treated this as a target, not just an observation. In 1971, Intel's first commercial microprocessor, the 4004, had 2,300 transistors. Each one was 10 micrometers wide, about the size of a red blood cell. The fact that we got from 10 micrometers in 1971 to 2 nanometers today, a 5,000-fold reduction in feature size, is the result of one of the longest sustained engineering efforts in human history. A useful analogy: if cars had shrunk at the same rate, a full-size pickup truck would now be smaller than a grain of sand. That is not metaphor. That is the math. And for most of that journey, the method was essentially the same. Shine light through a stencil onto silicon, etch away what you do not want, and repeat. The genius was always in making the light shorter, the stencil sharper, the chemistry more precise. Here is the first thing most people do not know. The light used to print modern chips is not visible light. It is not even ultraviolet. TSMC's most advanced machines use extreme ultraviolet light, EUV, with a wavelength of 13.5 nanometers, roughly 40 times shorter than the violet light your eye can detect. Generating that light requires heating a tiny droplet of 10 to 500,000 degrees Celsius using a high-powered laser twice. The plasma that results emits EUV radiation for a fraction of a second. This happens 50,000 times per second inside a machine that costs $350 million and is built by a single Dutch company named ASML. There is no backup supplier. ASML holds over 80% of the global market for advanced lithography equipment, and for EUV machines specifically, they have a 100% monopoly. A single EUV machine contains 100,000 parts, requires 40 shipping containers to transport, and takes over a year to install. Every leading-edge chip on Earth, in your phone, in a data center running ChatGPT, in a fighter jet, pass through light generated this way. The fragility of that single point in the supply chain is something governments are only now beginning to fully reckon with. The deeper revelation is what happens when you push below 3 nanometers. Classical physics stops being the right description. At 2 nanometers, transistor channels are so narrow that electrons no longer travel through them cleanly. They tunnel. Quantum tunneling means an electron can simply appear on the other side of a barrier it classically should not be able to cross. In a transistor, this causes leakage current, meaning the switch never fully turns off. It bleeds power and generates heat even in its supposedly idle state. This is why raw miniaturization stopped being sufficient around 2015. The industry's response was not to slow down. It was to go three-dimensional. Intel's FinFET architecture, now used across the industry, wraps the silicon channel into a vertical fin, giving the gate electrode 3 sides of contact instead of 1. TSMC's 3-nanometer process uses gate-all-around transistors, where the gate surrounds the channel on all 4 sides. Samsung calls their version MCFET. The physics of control improves dramatically because you are no longer fighting leakage from one direction. You are containing it from every angle simultaneously. The transistor count keeps rising not just because each transistor is smaller, but because the architecture itself has become three-dimensional. You are no longer paving a flat road. You are building a skyscraper. The actual manufacturing sequence involves over 1,000 individual steps. Start with a silicon wafer, ultra-pure, 300 millimeters across, grown from a single crystal so perfect it contains fewer than one defect per billion atoms. Coat it with a light-sensitive chemical called photoresist. Fire the EUV laser, project the circuit pattern through a reflective mask, and expose regions of the photoresist down to atomic precision. Develop the pattern, etch the silicon, deposit new materials, and repeat. Dozens of layers, stacked and aligned to within half a nanometer of each other. The alignment tolerance across a 300 millimeter wafer is comparable to tiling the entire surface of the United States with bathroom tiles and allowing less than 1 centimeter of total drift. The machines do this using laser interferometry and feedback systems that correct in real time. What comes out the other side is not just small. It is perhaps the most complex manufactured object human civilization has ever produced, made by the billions, sold for a few $100s. The complications are serious and compounding. First, heat. A modern chip running at full load dissipates 100 to 300 watts of power across an area smaller than a postage stamp. The thermal density exceeds the surface of the sun in watts per square meter. Cooling systems are now a primary design constraint, not an afterthought. Second, the economics are becoming punishing. Building a leading-edge chip fab now costs between $20 and $30 billion. That number is expected to cross $50 billion by 2028. Only a handful of governments and corporations can absorb that. The result is a dangerous concentration of capability in very few places, geographically and institutionally. TSMC's most advanced manufacturing is still heavily concentrated in Taiwan, a territory China has explicitly stated it intends to control. The CHIPS Act in the United States has committed $52 billion to domestic production, but TSMC's Arizona fab, as of 2025, is running about 2 years behind schedule. The engineering talent shortage is real and is not being solved fast enough. For you personally, this matters in ways that are already arriving. Every AI product accelerating through your industry, whether you work in healthcare, finance, law, logistics, or media, runs on chips produced by this process. The compute cost per AI query is dropping roughly 40% per year because of transistor density improvements. That means automation economics improve faster than most job transition planning assumes. If you work in a role where pattern recognition, document analysis, image interpretation, or data synthesis is a core function, the timeline you are probably imagining is too long. Beyond jobs, the geopolitical concentration of this technology means that chip access will increasingly be used as a foreign policy instrument. The U.S. export controls on advanced chips to China, expanded significantly in 2023 and 2024, are already reshaping which AI capabilities different nations can develop. Where you live will increasingly determine what technology you can access. In the next decade, the transistor will not disappear, but it will change form entirely. IBM has demonstrated functional 2-nanometer chips. The next battleground is 1 nanometer and below, where silicon itself may be replaced by materials like gallium nitride or carbon nanotubes that handle quantum effects more gracefully. Beyond that, researchers at institutions including MIT and Stanford are exploring 3D chip stacking, where entire processors are layered